AP Chemistry, Unit 4.5, Stoichiometry. Stoichiometry is used to predict the amounts of products or the amounts of reactants required for a reaction to occur. So some definitions that we'll need for stoichiometric calculations. Limiting reagent. The limiting reagent is going to be the reactant that is going to run out first. It's going to be the thing that is going to be capable of making the least amount of product. What will I run out of first? This is in contrast to my excess reagent. This is going to be the reactant that is going to be left over. I didn't have enough of the limiting reagent to react all of the excess reagent. And if the excess reagent had been allowed to produce as much as it could have, it would have made more product. Your theoretical yield is the amount of product that you could have potentially produced, assuming that you made absolutely no errors and the reaction completed perfectly and nothing was lost in the process. This is in contrast to your actual yield, which is going to be your actual amount of product that is going to be produced, and it can be used to calculate percent yield. Right here I have a diagram that is all of the relationships that can be used within stoichiometric calculations. This is called the map of mole land, and so you would go ahead and look here to find all of the different relationships that allow you to cross over and find the different pieces. So if you were given a mass of chemical X, you would use the molar mass of chemical X. That would get you to moles of chemical X. If you wanted to get to particles of chemical Y, you would use the mole-to-mole ratio to get you from moles of X to moles of Y. And then you would use Avogadro's number to get from moles of Y to particles of Y. And you'd be able to use this mole-to-mole ratio and the map of mole land in general to, again, identify which relationship you are needing for each conversion and to try to help guide you through your stoichiometric calculations. If you were given the problem, what is the percent yield in the reaction between 46.1 grams of cesium and 13.4 grams of oxygen if I was able to make 28.3 grams of cesium oxide? And that was what was collected. And then I have the balanced chemical equation here where we have 4 cesiums, 1 oxygen, forming a grand total of 2. My apologies there, I forgot to write the 2. 2 cesium oxides. Then you would go ahead and do a gram to gram calculation. So mass to mass, so mass of cesium to mass of cesium oxide that you would be capable of producing. So first I used the molar mass of cesium to get me to moles of cesium. I then used the mole-to-mole ratio between cesium and the cesium oxide, and then used the molar mass of cesium oxide to get me to grams of cesium oxide. And I was able to produce 48.9 grams of cesium oxide based off of that amount of initial cesium. I would do the exact same thing with my initial amount of oxygen as well. So again, same pathway, molar mass of oxygen gets me to moles of oxygen, mole ratio between oxygen and cesium oxide gets me to moles of cesium oxide, and then molar mass of cesium oxide gets me to mass of cesium oxide. I will then go ahead and compare the two potential outputs of these formulas, and I'm going to see that I have substantially less of the cesium oxide that can be produced based off of the amount of cesium that I have. So that means that the cesium is my limiting reagent, and this would be the maximum amount that I would be capable of producing based off the amount of reactants that I actually have present. I can then go ahead and calculate my percent yield. I was told I was able to make 28.3 grams of the cesium oxide, so part over whole divided by, theoretically, the max that I could have made, which was that 48.9 grams, times 100, and that gave me 47.9% yield.